In part A, we are asked to determine the potential difference between points A and B. We might begin by noticing that the current is flowing to the right in this diagram, and so we can already conclude that point A is going to be at a higher potential compared to point B. And that is simply because current will have a natural tendency to flow from a higher electrical potential to a lower electrical potential. Now, we're also told in this question that the entire section of this circuit from point A to point B is absorbing energy at a rate of 50 watts. That value is actually the power absorbed by this section of the circuit. So basically the question's telling you that the power is equal to 50 watts. Now, perhaps we know from this chapter that the power absorbed would equal the current multiplied by the potential difference. So all we need to do is solve this equation for the potential difference, and that's going to give us the answer to part A. And we can do that, of course, by dividing both sides of the equation by the current. So now we see that if we simply divide the power absorbed by the current that's flowing through this section, we would get the potential difference between the points marked A and B. Now again, the power was given as 50 watts, and the current is equal to 1 amp. So we'll just plug those numbers in. We'll have the 50 watts divided by the 1 amp, which of course works out to be 50. And the unit of potential difference is volts. So this would be the correct answer to part A. Now, given that the potential difference is 50 volts, we might imagine that at point A, the potential value there is 50 volts, and at point B, the potential value would therefore be 0 volts. Notice that would give a difference in potential equal to 50 volts as stated, or as determined in part A of this question. Now we need to determine the EMF of the battery. So what we're going to do is we're going to start at point A at a higher potential, and we're going to move our way through the circuit to point B. It might be a helpful metaphor to imagine going downhill, and you're starting at the top of the hill at point A, and then you are traveling to the bottom of the hill at point B. And at the top of the hill, the potential is 50 volts, and at the bottom, the potential is 0 volts. As you go down this potential hill, you will encounter a resistor marked capital R, and then you will also encounter the battery, and we are looking for the EMF of that battery. So starting at point A, we would have a potential of 50 volts, and then as we move through the resistor, there's going to be a drop in the potential. So we would say minus, and then the drop in potential across a resistor is always given by the current multiplied by the resistance value. So that right there is the quantity delta V across the resistor. So that's the drop in the potential. And then we continue down our potential hill, we encounter the battery, there's another potential drop, and that will simply be the EMF of the battery, as measured in volts. And by the time we get to the bottom of our hill, the potential value is 0. So we're looking for the EMF of the battery. All we have to do is add the EMF to the right-hand side of the equation. So now we can see that 50 volts minus IR will give us the EMF of the battery, and we know the current was 1 amp, and the resistance value was given to be 2 ohms. So we'll plug that in as well. And of course, if we work this out on our calculators, we would get 48, and we calculated an EMF, so that would be in the standard unit of volts. So this would be the correct answer to part B of the question.